Hi everyone. Today my group is going to discuss about impact test, failure of the Liberty ships. Let us understand the historical background. During World War II, there is a tremendous usage of resources such as ammunition, food, oil, and fuel. In 1940, in order to support the battle, the United States started an emergency shipbuilding program. Over 2,700 all-welded lightly armed cargo ships, tankers, and other vessels, known as the Liberty ships, were produced. In this program, there are some problems. First, the design of the ship. The ships were to be all welded rather than riveted to increase the cargo capability of the vessels and accelerate the production process. However, there are some problems. Numerous vessels suffer sudden fracture, some of them being split in half. They are caused by some factors. First, welds produced by largely unskilled workforce contain crack-type flaws, which act as stress concentration. Second, welding is a hydrogen embrittlement. Lastly, ship steel has fairly poor choppy impact tested fracture toughness. In this case study, there are two ships will be discussed: John P. Gaines and Scanhan Neck Daddy. Before further explaining failure analysis, let us understand the theoretical background on fracture mechanics. There are two failures: ductile failure and brittle failure. Ductile failure is a combination of stress and crack length leading to unstable crack growth and catastrophic failure. It's associated with large amounts of plastic deformation, and localized necking or distortion is often present. Next is the brittle failure. It is characterized by rapid crack propagation, occurs with sonic speed, and perpendicular to the applied tensile stress. There are some factors promoting the failure. First, low temperature, causing ductile to brittle transition. High shrink rate do not allow time for stress distribution. Third, deep notches, which create constraint at the crack tip.
Principles of fracture mechanics are important, and it is related to design using fracture mechanics, stress concentration, fracture toughness, and impact testing. Design of critical structural details for reduction of stress concentrations use fracture mechanics principle. Stress concentration is a property to determine fracture toughness. It amplifies applied stress at tips of flaws. It causes localized area of high stress, which contributed to the brittle fracture of the ships. Fracture toughness is the ability of a material containing a crack to resist further fracture. Fracture toughness decreases with increasing notch acuity, which is sharpness. For impact testing, it will be discussed later. In brittle materials, when maximum stress greater than critical stress, crack propagation will occur. There is an increase of crack size and stress concentration. A propagating crack in brittle material cannot be stopped and will proceed through the entire structure. There is a formula to find critical stress, which is as shown below. There are two figures, which is on the left is the geometry of surface and internal cracks, and on the right is schematic stress profile of internal crack along line X and X apostrophe. Generally, there is a relation between fracture toughness K, critical stress, and crack length. The equation is written as follows. So, in designing any structural, it's preferred to avoid using sharp corners.
So, my name is Muhammad Afifi. I will explain the ductile to brittle transition temperature. Ductile to brittle transition temperature. By definition, the choppy impact energy is the average of the maximum and minimum values. The fracture surface appears to be ductile Pure metals commonly have defined transition temperature. Almost all BCC and HCP metals also commonly have defined transition temperature. Alloys, the transition can occur over a range of temperature caused by the difference of elements in the material. This is an example of what a DBTT ductile to brittle transition temperature graph would look like. Sets of data from impact test, Sharpie or result are tabulated into a graph. Temperature on the x-axis, energy absorbed or force applied on the y-axis. We can see a difference in the ductile region and the brittle region clearly, in which the ductile region happens at a higher temperature and vice versa for the brittle region. In the middle of the two regions are the transition temperature, average of the highest and the lowest points. As we can see for different materials, there are different results based on their properties. Copper, which is an FCC structure, forms a straight line in which shows that in the range of temperature, it will always provide with a ductile failure. Comparing this to the mild steel BCC structure in which the transition temperature is clearly seen as well as the ductile and brittle region affected by the temperatures. Shown zinc and nylon specimens are also provided with different results based on their properties. A good range of transition temperature gives a warning before failure will occur in changes of temperature. As for our case study, the material used for the Liberty ship are commonly mild steel, in which most modern ship uses 0.23% carbon steel for balance of ductility, in which shown by the graph, low carbon steel have a high ductility even in low temperatures and changes drastically over a small range of temperature changes, leaving no warning. High carbon steel have a high brittleness for most temperature changes in which is not fit for construction that needs to handle a high amount of load.
In order to measure the toughness of the ship steel, impact test is carried out. Impact test is a test that used to measure the resistance of a material to rapidly sudden applied loads. There are two types of impact test, Sharpie test and ISOT test. For the Sharpie test, the test material is placed horizontally. The notch is positioned away from the striker. Whereas for the ISOT test, the test material is placed vertically. The notch is facing the striker. So how do we measure the absorbed energy? Firstly, a hammer is released from position H1 to hit the specimen. Then, the pendulum with a knife edge strikes and fractures the specimen at the notch. The pendulum will continue to swing and rise to a maximum height of H2. The difference in the height or also the potential energy of the pendulum is equal to the energy absorbed during fracture. Also note that the materials that have high toughness will absorb a lot of energy when fractured, whereas brittle materials absorb very little energy. Here is the step for the Sharpie test. From the diagram, we can see how the specimen is placed, and the main structure for the Sharpie test is the hammer, anvil, and also the skew. Firstly, the specimen is placed onto the support with notch facing back side of the striking direction. Then the notch is placed at the center in between the anvils. The pointer is placed to read 300 joules. Next, the hammer is locked and released. The amount of energy consumed is indicated by the pointer.
So I will give a further explanation on what actually happens that leads to the catastrophe on the US Liberty ships. So there are a few reasons that lead to the brittle fracture that causes the ships to be cracked into half. The first one is due to the steel quality, and the second one is due to the poor welding. So back in the days, they normally used timber or wood for ship constructions, but in this case, they chose steel plating as the material for ship construction. Since plating for ship construction is a bit new at the moment, so the supply for the high-quality steel was barely available during World War II. The steel used for this construction must be able to experience ductile to ductile transition. This is because the ships will be deployed to the North Atlantic that will change the steel from ductile to brittle, thus exposing it to ductile fracture as the temperature dropped below the transition temperature. The material selection and the specification of steel for hull were based on the tensile strength, heel point, and an unusual measure of elongation. In spite of the steel failing the brittle fracture, it actually passed the standards of the day, location-to-location variability for the rim steel. Other than that, in this case, the steel used did not comply with the modern impact absorption standard. The steel were also under a multi-axial stress in the surrounding of the cargo hatches. This promotes the rising of the ductile to brittle transition temperature, particularly under high strain rate loads such as the impact of heavy sea. And now we will move on to the next figure to explain a little bit about multi-axial stress. The state of stress and strain at a point in the body can be described by 6 stress components: X, Y, Z, XY, XZ, and YZ, and 6 strain components X, Y, Z, XY, XZ, and YZ acting on orthogonal planes X, Y, and Z. Stresses and strains acting in other direction or plane can be found by using transformation equations or graphically by using Morse code. As we can see, the stress doesn't only come from 1 dimension or 2 dimension and even from 3 dimension. It actually comes from all dimensions. Next, we are going to discuss about the poor welding, which is another reason to failure. Liberty ships were all welded construction, which was a new technology at the moment. The shortage of skilled workers is the reason why insufficiently trained personnel were employed as welders, thus resulting in poor weld quality. The flaws in the welds acted as stress raisers, causing the fracture to start. Besides, the metal was also exposed to hydrogen embrittlement due to poor welding, which is another reason for the failures. Hydrogen embrittlement is a metal's loss of ductility and reduction of load-bearing capability due to the absorption of hydrogen atoms or molecules by the metal. The result of hydrogen embrittlement is that components crack and fracture at stresses less than the yield strength of the metal. Hydrogen embrittlement is mostly caused by electrode welding in wet or damp conditions. The figures below shows how the process of hydrogen embrittlement occurs. At room temperature, hydrogen atoms can be absorbed by carbon steel alloys. The absorbed hydrogen may be present either as atomic or molecular form. Given enough time, the hydrogen diffuses to the metal grain boundaries and forms bubbles at the metal grain boundaries. These bubbles exert pressure on the metal grains. The pressure then can increase to the levels where the metal has reduced ductility and strength. And next, I will show you the example of microstructure of a metal that is exposed to hydrogen embrittlement. These 3 figures show the scanning electron microscope images of intergranular cracking in a steel screw due to hydrogen embrittlement.
Hi guys, I am Mahesh from Group 3 and I would like to present the conclusion for this impact test. In the first slide, we can know that from this test, we can conclude that ductile transition temperature is the minimum temperature in which a given material has the ability to absorb a specific amount of energy without fracturing. From the Chappie test conducted, we know that a material's ductile ability decreases as the temperature decreases. Moving on to the second slide, this slide explains the uses of impact tests, namely to show a ductile brittle transition for low strength materials. Here we can also see that ductile brittle transition plays a vital role in the fracture mode of a material, for example BCC transition metals. Usually, materials with low impact energies are of high strength. Also taking account that high strength materials are usually insensitive to high temperatures. This is the gist of the last slide. Thank you.